The calorimeter allows us to measure the heat of many substances. In the lower right corner, you can see a picture of a typical coffee cup calorimeter. It is simply just two nestled styrofoam cups with a cardboard cover, and there's a small hole in the cardboard cover so a thermometer can fit through it. The calorimeter works on the premise that the amount of heat released in a reaction, or by a metal, would be the same amount of heat that would be absorbed by the water that is surrounding the reaction, or the metal. So down in the lower right corner, I'm going to go ahead and just show you that if the blue dot was the metal and it started releasing heat, you can see that the water would start to absorb that heat. So we use the idea of Q for heat. The Q metal is equal to the Q water in this example. Remember that the negative sign means released. So the metal is releasing the heat, and the positive sign means absorbed. So the water is absorbing that same amount of energy. The cover is there to prevent any of that heat leaving the calorimeter, and we assume in a coffee cup calorimeter that all heat loss is negligible. We then simply use the equation Q is equal to m times C times delta T, and we can plug that in on both sides of this equation. So I'm going to get m times C times delta T, and this would be of the metal, and that would be equal to m times C times delta T of the water. And one of the variables will be a missing piece, and you just solve for the unknown. So let's take a look at this calorimeter example. Let's say I put a piece of aluminum metal that has a mass of 10 grams. We don't know its specific heat, and I'm going to tell you that I'm going to heat it up in a Bunsen burner flame until it's about 150 degrees Celsius. Okay. Heat transfer means that the heat energy from the flame will go into the metal, and the metal has a temperature of 150 degrees Celsius at that point. I have water, and let's say I have a 200 gram sample of water, and the specific heat of water is 4.184 joules per gram Celsius. And we're going to say that the initial temperature of the water is very close to room temperature, and so we will say 25 degrees Celsius. When I place the 10 gram sample of aluminum into the water, there's a temperature difference. And so the first thing I will notice is that heat will transfer from a hotter temperature object to a lower temperature object. As that's happening, the thermometer in the water will change. It will actually start to go up. It's only going to go up by a small amount because remember, water has a very high specific heat. Let's say it goes up to 28 degrees Celsius. The metal is actually going to also become 28 degrees Celsius as well. So as the metal is releasing the heat and the water is absorbing the heat, eventually they'll reach thermal equilibrium. And that is when the two temperatures are the same, and that's when heat transfer stops. So we're going to go ahead and we're going to add the final temperature, and it will be the same for the metal and for the water. All we have left is the math. So remember that the amount of energy that the metal released is going to be equal to the amount of energy that the water absorbed. And we know that the Q is mc delta T. And we're going to go ahead and put that on both sides of the equation. So now we're going to pop in the numbers. So for the metal, we have 10 grams. We're solving for C. And the delta T is going to be the T final minus T initial. So that's going to be negative 130 degrees Celsius. Remember, there is a negative on this side, so when I multiply these together, I will get positive 1300, and then our C is what we're solving for, is equal to, and now on the other side, we're going to take the mass of the water, which is 200 grams. We're going to take the specific heat of the water, which is 4.184 joules per grams Celsius, and the delta T, which is going to be 28 minus 25, which will be 3 degrees Celsius. That gives us 25, 10, and everything's going to cancel out except for the joules. And over here, the 1300, remember that's actually grams in Celsius as well. Pop that in there. And then I'm going to solve for C. So I'm going to divide both sides by the 1300 grams per Celsius. And that would give me a C of about 1.93 joules per grams Celsius. Alright, so let's try another problem without the visual. We have an unknown metal that has a mass of 17.19 grams. I have a initial temperature of 92.50 degrees Celsius of that metal. I've been told that my sample of water is 25 grams, and it has an initial temperature of 24.50 degrees Celsius. The last statement in the question tells you the specific heat of water is 4.184 joules per gram Celsius. And they tell you right above that the final temperature of the system is 30.05 degrees Celsius. So remember, when the final temperature is reached, that will be the final temperature of both the water and of the metal. And so we're trying to solve for the specific heat of the metal, and so that you can see that right here. We know Q metal, and that's going to be releasing the heat because it's warmer than the temperature of water, will be equal to Q water. We want to make sure that our signs are there to work through in the problem, and we're just going to go ahead and put in the numbers. So I'm going to take the 17.19, I'm going to leave out the units. We're going to do C, and we're going to do the change in temperature. We get final minus initial, negative 62.45, and that's going to be equal to 25 times 4.184, and the temperature change of 5.55. Instead of solving this problem simultaneously like I did in the last example, I'm going to go ahead, since I know all three of these values, and get the Q of the water, and that is 580.53, and I'm just going to make that equal to this side of the equation now, which is 17.19 C times negative 62.45. Remember that there is a negative sign out here. You can see that up here. And we're going to multiply 62.45 times 17.19. That gives me 1073.5155 C is equal to 580.53, and then I'm going to solve for C by dividing both sides by this number. And C will come out to be 0.541 joules per grams degrees Celsius. You could then use your reference table to identify the unknown metal based on the specific heat. We've got one more problem to look at. I want you to try this one on your own, and when you come back I will have the setup and I'll just quickly go over the answer. Alright, so let's take a look at this problem real quick. We have a sample of vanadium. We know its mass is 32.07 grams. We know it was heated to 75 degrees Celsius. That is its initial temperature. and we know that the final temperature was 26.30 grams. Remember that the final temperature is for both the metal and for the water. The initial temperature of the water was 22.50 degrees Celsius. They give us the specific heat of vanadium and water down below, and they want us to come up with the mass of the metal. So I started off, as always, with the Qm is equal to Qw. Since the metal is a higher temperature than the water, the metal will release the energy into the water, so it's negative Q is equal to positive, negative Qm, is equal to positive Qw. We know Q is mc delta T, and so I just plugged in the numbers and did the math algebraically, and the answer came out to 48 grams. Take a moment to take a look at this. Make sure you're using your calculator, you're understanding where all these numbers are coming from, because you will have to do this in class in a lab.